All right, just a little bit to touch on these aluminum and iron oxyhydroxides. Notice that there is only aluminum. This is basically going to be a 2-to-1 clay layer, or I'm sorry, an octahedral and an octahedral combined together with these hydrogens. So there's nothing else that can fit in here. These are going to have more anion adsorption because we're going to have these Al3 plus, and that is going to be the only charge that is left. So we can hold on to more of our anions. And when I'm thinking about these particular types of soils, these are the ones in the video where they were talking about positively charged soils. So in places like Brazil, South America, where they have high temperatures, they get enough rainfall. Those soils are old, they've been weathered, all the nutrients are gone out of them. One of the problems that they have is phosphate absorption, adsorption with a D, right? So this anion adsorption. So the problem is that those pHs are also very low. And the lower the pH, the greater that adsorption is going to be. So they throw tons of lime at it and nothing happens because it has such a strong buffering capacity that there's nothing for this to change. So if you're dealing with, you know, gibbsite or goethite or hematite, if you start getting into these soils and you can't figure out why you are not able to uh, grow any plants, it's probably because there's no cation exchange capacity. There's only anion exchange capacity. All right, so the next one that we're going to talk about is this humus. And so humus, this is organic chemistry. This is one of those molecules. I am not an organic chemist. I do know that these structures take a lot to identify and that these phenolic rings are very difficult to break. So along with all of these, there are going to be both positive and negative charges on this in various places. And that is going to be based on how these charges or the actual bonds change within this structure. But overall, it's going to be a net negative. Remember that our humus has like a CEC somewhere between -100 and -500 centimoles of charge per kilogram. And that they're going to have both hydrophilic and hydrophobic tails in here that are going to influence the water holding capacity. All right, so here we are with our isomorphic substitution. And so isomorphic substitution is permanent charge. We cannot change this. This actually happens when that rock formed coming out of that volcano. From our igneous rock, whatever type of rock that it was that formed, even our sedimentary rocks, or even our metamorphic rocks. When that magma cools, whatever elements are in there, when that crystal forms, that's all there is. So as I spoke before, isomorphic means similar size and shape. Has nothing to do with the charge. We actually need a different charge in order to get our permanent charge. So the thing we need to know is that in the tetrahedral, we're going to replace this silica 4 plus with this aluminum 3 plus. And when we make that change, the soil or actually the charge in this tetrahedral layer will become more negative. In our octahedral layer, aluminum 3 plus will be substituted by magnesium 2 plus. Now we can't have a magnesium 2 plus substitute for a silica 4 plus in the tetrahedral. This is the only substitution that we have. Silica 4 plus being replaced by aluminum 3 plus, aluminum 3 plus being replaced by magnesium 2 plus. This only occurs in the octahedral. This only occurs in the tetrahedral. All right, so let's take a look at this overall kind of isomorphic substitution. So oxygen so we're going to look at the tetrahedron. Oxygen has a charge of -2. And if we have 4 oxygens, then that overall charge is going to be -8. our positive charge is going to be silica 4 plus. So we would have positive 4. The overall net charge on this particular or specific tetrahedron is negative 4. For our octahedron, again, we have our oxygens that have a charge of negative 2. We have 6 of those. So our negative charges, our negative charges are negative 12. Our aluminum is plus 3. Positive charges are plus 3. The overall net charge on this tetrahedron or octahedron is negative 9. So together, this think about this as a 1-to-1 silicate clay. So like kaolinite, if this were attached to each other, the overall net charge on just this particular, imagine if that was just this particular portion of that 1-to-1 clay mineral, that overall net charge would be negative 13. All right, so let's put all this together. We have our 1-to-1 clay layer. Our tetrahedron is going to, we have 3 tetrahedrons here. We add up all of the oxygens, so 2, 4, 6, 7, 5 is 12, and 5 is 17. Each oxygen has a charge of negative 2, so our overall negative charge is going to be negative 34. 17 times negative 2. We have 3 silica 4 plus, and we have 4 aluminum 3 plus. So this is plus 12. This is plus 12. Negative 34 plus 24. The overall charge on this particular portion of that 1-to-1 clay mineral is negative 10. And what I'm trying to do is set you up to understand what happens if we were to make this isomorphic substitution. All right, so let's look at this here. We have another 1-to-1. This is a 2-to-1 clay mineral. Along the top, we have our oxygens, 2, 4, 6, 7. That's going to be negative 14. Go ahead and open this up. All right. In the middle, we have plus 12. 3 silica. When we get to our octahedral layer, 5 oxygens, each with a charge of negative 2. 4 aluminums, each with a charge of plus 12, or total charge of plus 12. Again, 5 more oxygens. So negative 10. Here is our bottom 1-to-1 clay layer, our tetrahedral. We have plus 12. And then on the bottom, 7 oxygens, each with a charge of negative 2. It's negative 14. When we add all these up, the overall net charge is negative 12. Now, pause the video, do the other side, and see what the difference is. All right, so we come back. We'll look at this again. We have pretty much the same structure, right? So we know that our oxygens are each worth, or have a charge of negative 2. So we have 7 oxygens on the top, negative 14. We've now substituted aluminum for silica, which means now this charge inside of this inside of this tetrahedral layer is now plus 9. not plus 12. The oxygens are all going to be the same, right? They're not going to change. So now inside of this octahedral layer, we have substituted magnesium for aluminum, and now our charge is plus 8. Next, we substituted again aluminum for silica, and now our charge is plus 9. So previously, if we had just a basic general 2-to-1 clay layer, we would have a charge of negative 12. When we do isomorphic substitution, we actually now increase that charge, or actually the charge becomes more negative. I'm going to use terms like more negative and more positive when I'm discussing this isomorphic substitution and especially pH dependent charge. So by doing this isomorphic substitution, or this, we can't do the isomorphic substitution. And this happened when that mineral was formed. If there is isomorphic substitution, that is how the charge is different on different types of soil. Okay, so that is permanent charge. We cannot influence that. I can't go out and apply more aluminum. Let me go back to that. I can't go out and apply more aluminum and magnesium and change the overall charge of this soil. That is what that soil is. When it was formed, whether there was a silica or an aluminum or magnesium inside of that structure is how that soil formed. That is the permanent charge. The thing that we can influence, and this is why organic matter is so important, is the pH dependent charge. And there are 3 components to pH dependent charge: functional groups of organic matter, aluminum and iron oxides, and broken edges of clay. Now, we're not really too concerned with this aluminum and iron oxide of these broken edges of clay, especially the broken edges of clay. Like, you need an electron scanning microscope in order to see where you broke one of these edges of clays. And we don't really deal with too many aluminum and iron oxides because those are going to be highly weathered soils. But the things that we can influence are going to be this organic matter. And these functional groups of organic matter, now you don't need to know that this is a carboxylic group, but we are going to understand how this hydroxyl on the end of this influences or changes the cation exchange capacity, or increases the CEC, makes this soil more negative and can hold on to more positive charges. Okay, so as much chemistry as I'm going to get into here, the things that we need to know about pH is that when a soil is more acidic, it has a greater hydrogen plus concentration. When we add lime, soils become more alkaline, meaning it has a greater OH negative or hydroxyl concentration. More acidic, more hydrogens. More alkaline, more hydroxyls. So in this particular situation, we have applied lime and our soil has become more alkaline. Now, I'm not really sure what the pH of this particular demonstration is. All I know is that the soil has become more alkaline. So let's say the change between 6.5 to 7.5. That soil has become more alkaline. All right, so I have these hydroxyls in soil solution. I have these functional groups of organic matter. Now, because these hydroxyls have a negative charge, they are looking for, I'm doing air quotes, they're looking for a partner. They're looking for another hydrogen to give it the equilibrium or the stability to be a water molecule. Now, I'm not talking about a water molecule as in like you can actually mine or extract this water out of the soil and drink it. I mean like a water molecule as in 6.02 times 10 to the 23rd. as in one of those little molecules. So as our soils become more alkaline, we increase this hydroxyl concentration. Because this hydroxyl is looking for a partner or to become in equilibrium, this hydrogen will dissociate from that functional group of organic matter and form a water molecule, very small water molecule. When that happens, notice that there is now a negative charge on our what used to be that functional group of organic matter. Let me go back. It's nothing more than the hydrogen dissociating from this functional group of organic matter, binding with this hydroxyl to form an equilibrium and a stable water molecule. It's nothing more than a dissociation. When that hydrogen dissociates, we actually increase the amount of negative charges. And if you remember from the previous one, we have these negative charges over here as well. So this dissociation from that functional group of organic matter forms this water. All right, cool. So we've increased our CEC by adding lime. So that's one of the benefits of adding lime, is that I've kind of increased the size of my cup. So now I can apply more fertilizer and I can hold on to that fertilizer. So we have this, we've got 5% organic matter. We have all of this dissociation from those functional groups. We've increased our CEC. We've applied enough fertilizer. When we apply that fertilizer, what happens is there are transformations, and we'll go over this in module 4. And if you take me for fertility, we'll go over this even more as to how that pH actually changes. So we have all of these functional groups of organic matter. That hydrogen has dissociated. We apply fertilizer, and now our pH becomes acidic. And remember that acidic soils have a greater hydrogen concentration. So whereas we once had these negative charges, as we start to increase the hydrogen concentration, that hydrogen will then protonate, or it will reassociate, protonation and reassociate with this functional group of organic matter, or this negative charge here. So now we're back to balance, right? Notice that we're back to balanced here with these functional groups of organic matter. So as our pH decreases, what do you think happens to our CEC? It decreases. As pH decreases, CEC decreases. As pH decreases, CEC decreases. As pH increases, what happens to the CEC? It also increases right here. When pH increases, the CEC increases. When pH decreases or becomes more acidic, CEC decreases. Remember, we can only influence these functional groups of organic matter. Now, what happens is that as our pH gets very acidic, that as we kind of over increase this hydrogen concentration, we can have what we call a protonation. So we have a very high or very elevated hydrogen concentration, and it's possible that that hydrogen can protonate this functional group of organic matter, giving it a positive charge. And so this is kind of what happens in our ultisols, or our Gibbsite as well, that if we have too much of a acidic pH, we can now start to have more positive charges in our soil. But we don't want positive charges. Remember, we want them to be negative, because negative charges hold on to cations. And cations are the primary ions that get taken up by plants. So if we start to have more acidic soils, we can start to have more positive charges in our soils, which is not going to go well. It will then hold on to our anions. And we typically want cations to be taken up by plants. You might have to watch that again to understand that as the pH increases, what happens to the CEC? It increases. As pH decreases, what happens to the CEC? It decreases. All right. I'm gonna return to that when I start talking about the difference between cation exchange capacity and anion exchange capacity. All right, so we talked about adsorption with a D, and this is going to be this attraction and release of these different ions or cations. So for our cations, a few of our anions, these are going to be what we call diffuse ions, and they're going to move by diffusion. So that as the concentration in the soil gets less, these ions will then move in that direction. We have two different types of complexes. We have an outer sphere complex, and this outer sphere complex is going to be easily exchanged because there's kind of this water molecule that is sort of acting as a buffer that kind of minimizes the charge. That charge is not as strong. I think about this kind of like a hula hoop. And then if two people had a hula hoop and they were trying to bond with each other, that hula hoop is causing a little bit of a gap, and that bond might not be as strong. So we have this water molecule that is kind of diluting the charge or kind of minimizing that charge, and it's not held to that soil colloid very tightly. So outer sphere complexes, not held very tightly. Inner sphere complexes, however, are held very tightly. And there is no water molecule around that. So imagine taking the hula hoop, and then now these, I'm just using humans and hula hoops. Now you take two humans with hula hoops trying to form a bond, the hula hoops kind of stop that reach. With inner sphere complexes, there is no hula hoop, and I want you to think about these two humans actually locking arms. Now that's a very strong bond. That's going to take a lot to break that bond. So these are more strongly adsorbed to the soil colloid. So let's take a look at that. Here we have an outer sphere complex. So we have our calcium 2 plus that has this water molecule around it. And when it adsorbs, it is going to adsorb with hydrogen bonds to this tetrahedral. Now, I know I've mentioned before that hydrogen bonds are very tight bonds, but because it's attached with this water molecule, it's going to be a little bit less. So this can easily be desorbed off of that soil colloid. Next, over here we have phosphate, and notice that phosphate will now bind or bond with this tetrahedral, but this is actually a covalent bond. The covalent bonds are very difficult to break. They share those outer electrons. And so here we have hydrogen bonding. It's really just kind of stuck to this hydrogen. This is actually bonded with that hydrogen. So that covalent bond is going to be where I mentioned that that two people locked arm in arm is going to be a very tight bond to break. Just a little bit about some of these cation exchange reactions is that it is going to take a 1-for-1, one charge in soil solution to bind or to adsorb or desorb to exchange with one positively plus ion. So this could be sodium, it could be ammonium, it could be potassium, going all the way back to that lyotropic series. Or we can have charge equivalence in that it takes two hydrogens to dissociate one calcium. So notice that it takes 2 hydrogens to dissociate. And so now that calcium 2 plus is now inside of the soil solution and can then be taken up by the plant. So here we have a look at that. We have our plant. We have our soil colloid that has these various cations that are adsorbed with a D to these negative charges. And notice that 1 K plus to one of those charges. We have copper 2 plus that is adsorbed by these 2 charges. Magnesium 2 plus adsorbed by these 2 charges. So one of the things, and I've mentioned this before, that it is not likely that a plant with a B absorbs ammonium and then gives it back out. However, it does release hydrogens into the soil. When it releases these hydrogens, remember that it takes 2 hydrogens to displace or dissociate one of these calciums. So these 2 hydrogens are in soil solution. They are looking to bind with these 2 plus negative charges. So 2 plus, take up 2 negative, desorbs this calcium, and this can now be absorbed with a B into the plant. And so that is this back and forth kind of dance, if you will, or exchange between plants and the soil colloid in order to get the nutrients that it needs. We also have this ratio law where it can only be adsorbed in different ratios. Here you can see that we have 20 calciums and 5 magnesiums. And this ratio is actually like a 4 to 1. And notice that this is a ratio of 4 to 1. Again, back to our lyotropic series. We've been over this before. This is going to be the strength of adsorption with a D to our soil colloid. And this is going to be affected by the charge and the hydrated radius. So the greater the charge and the smaller the hydrated radius, the tighter that cation is held to that soil colloid. So aluminum has a very high charge and a very low hydrated radius, or a very small hydrated radius. Now, calcium and magnesium both have the same charge, but calcium has a smaller hydrated radius. Therefore, it is adsorbed to the soil greater than magnesium 2 plus. And then finally, for these have a low charge, and their hydrated radius influences kind of the adsorption. So sodium is going to have a very low charge with a very high or large hydrated radius. Sodium and water do not mix well. One cool thing that you could do is YouTube sodium and water, and you'll see that when you put sodium in water, it causes an explosion. There's a big reaction that happens between sodium and water. So this lyotropic series is going to be influenced by the charge and then also the hydrated radius. So high charge, small hydrated radius, held tightly to the soil colloid. High charge, low hydrated radius, held tighter to the soil colloid. Low charge, large hydrated radius, not held as tightly. Then there are also complementary ions, and this is just kind of, this really starts to get into the ratios. If we start getting into like real soil chemistry as to how these ions are held and what is the balance between the soil solution, not really so much that you need to know about these on the exam, but just to be aware that there are some other laws that govern how these different cations are adsorbed to the soil colloid. All right, So back to cation exchange capacity. I just want to drive this point home about pH and cation exchange capacity. So here we have our sandy loam soil, low surface area, low CEC, cannot hold on to a lot of cation. So this is going to be more like our maybe 1-to-1 kaolinite, our very small cup, or if we had our clay soils, maybe a montmorillonite or a smectite, that now we're starting to get into a CEC of about 25, we can hold on to more of these cations based upon the Liotropic series. This is more like our large cup. So when you send your soil sample in, they will measure two types of CEC. They will measure the effective CEC. So they'll mix it with water, they'll test the pH, and that is going to give you the effective CEC. They'll use a buffer CEC, which means they will increase the soil pH. And so remember that as soil pH increases, what happens to the cation exchange capacity? It will also increase. So they will raise this to either a pH 7 or a pH 8.2 so that we influence those functional groups of organic matter. And so here we go. That now we're into our pH dependent charge, and this is why it's so important, because in acidic soils we have a lower or a less CEC, so our cup gets smaller. If we want to influence that, we will apply lime and increase the pH, that as our soils become more alkaline, and this can even be a change from 5.5 to 6, we will increase our cation exchange capacity. One of the other ways that they'll measure kind of a measurement of the cation exchange capacity is the percent base saturation. If we were in soils 3000, then we will kind of go over this. And all this is what is the cation exchange capacity and the ability to hold on to some of these more basic cations like calcium and magnesium. Calcium and magnesium are in lime. So what is going to increase the pH? Also, this influences our anion exchange capacity, so that as our CEC increases, the AEC decreases. So if we have a more acidic soil, we were going to have inner sphere complexes for these particular anions. And as I mentioned before, we're going to see these in highly weathered soils that are acidic, mostly like in our tropics. So like in our equator, those zones that are in the middle of the equator, I'm thinking like Central America, starting to move into like the northern part of South America. Those are going to be highly weathered. And when I think about those, I'm thinking of like maybe Georgia. Georgia has some highly weathered soils, that red clay. When I'm seeing that red clay, I'm seeing highly weathered soils that are likely to be acidic, that are going to have a high anion exchange capacity, because there's just nothing left to adsorb any of the other cations. This also plays a role in kind of our pesticide and groundwater contamination. So we're going to end up ultimately using soil in order to pull out some of the contaminants that are in our ground, or at least in our rain supply. Remember that we talked about soil being this sort of water filter. So it is going to filter out some of these contaminants. All right. So the CEC is going to influence a lot of the adsorption of our different molecules, right? Could even be biomolecules. And so one demonstration of this is that we have our kaolinite, which has a low CEC, probably about -3 to -15. And then we have a montmorillonite. And remember, montmorillonite is going to have a high shrink, at least a high expansion. It's going to expand when we add water. It has a high surface area. It also has a high CEC. So they added this Bacillus thuringiensis, and you can see how much was actually adsorbed to the soil. And that is because of the cation exchange capacity. So soils with high CEC are going to not only influence fertilizers, but they're also going to influence pesticides and herbicides. We'll look at this in the next slide. All right. So here they have applied this herbicide to try and kill some of these weeds. They applied this, a broadcast application of this herbicide, and it seems to work well for the most part. But what happened here? How come it didn't work on these? Well, it turns out that when they kind of developed this land, what they did was when they bulldozed, they brought up some of that clayey subsoil, which had more cation exchange capacity. They brought up this cation exchange capacity because there were more clayey subsoil. And so that clay is going to have a greater CEC, and the herbicide was actually adsorbed to that clay molecule. So you might see on a pesticide or a herbicide label that'll tell you if you have a specific soil type or your CEC, you will need to apply extra so that you don't have this issue. And so that's just kind of another real world explanation of where you may or may not run into this thing about cation exchange capacity. And then just to look at some of these different partitioning coefficients. If we were in a herbicide technology class, this might play a role. But we can see that as, there are different, the organic matter influences how much of that herbicide is actually adsorbed. So for this organic carbon, notice that we have like 609, and that is going to actually hold on to more of this hydroxyatrazine. So if you were in herbicides, this is where cation exchange capacity might come into play for that. All right, so this is going to end module 1.2.2. Next, we will move into soil classification.